Well, hello everybody. Thank you for being here for this latest session in the Humanities Centre's series on the idea of truth. Thus far, our focus has been almost exclusively philosophical, but today we begin looking at other disciplines, starting with the realms of mathematics and the natural sciences. And here to lead our discussion are three splendid professors, drawn from our wonderful faculty in the College of Arts and Sciences. So at the far end of the table, Dr. Ron Kaufmann is Professor of Environmental and Ocean Sciences, as well as the college's Associate Dean and Director of the Marine Science Graduate Program. He was educated at the University of Minnesota and received his PhD from UC San Diego. Among his research interests is the investigation of marine communities in extreme environments, such as the Antarctic and the deep ocean. It also has to be noted that Ron is a member of the three-person Humanities Centre Steering Committee and has played an absolutely central and vital role in getting us off the ground here and keeping us up in the air. So always thanks so much, Ron, for that. Dr. Mitch Malachowski is Professor of Chemistry and Biochemistry and has been a member of faculty at USD since 1984. He received his PhD from the University of North Carolina, Chapel Hill. And in addition to his work on metal organic frameworks, Dr. Malachowski has research interests in the history and philosophy of science and on the relationship between teaching and research at predominantly undergraduate institutions. He's been the recipient of many awards and in 2014 was named the Case Carnegie Foundation California Professor of the Year. Finally, Dr. Candice Price is Assistant Professor of Mathematics. She received her PhD from the University of Iowa and before coming to USD in 2016 held positions at Sam Houston State University and the United States Military Academy at West Point. Her research interests lie in math modeling, knot theory, DNA topology, and computational biology. I'm really completely out of my depth. I have no idea what I said about any of that. Dr. Price has been the recipient of a great many awards and fellowships. She's been a National Research Council Davis Fellow, and in 2013 was named Janice A. Lumpkin Educator of the Year. Please join me in welcoming today's very special speakers. Thank you very much.
Ryan, thank you very much for the very kind introduction. What we're going to try to do, at least what I'm going to try to do, is start off with sort of an overview of how people in my area, and I in particular, think about truth in science. And then Candice will speak next, talk about truth in mathematics, and then Mitch will take us home with some actual 3D models, which I can't claim to have thought of. So I'd like to start off by saying that even though I've been thinking about this topic for a little while, the notion of truth in science actually catches me a little bit flat-footed in the sense that in my area of science, we don't really think or talk in terms of truth very often. We think in terms of hypotheses, we think in terms of facts, knowledge. We want to make sure that there's evidence in support of those. But we don't really frame that in the context of truth. And so rather than sort of go down a philosophical path toward explaining what a philosopher would think of as truth and how a scientist might view philosophical truth, I'm just going to try to talk about knowledge and knowledge acquisition and facts and those sorts of things within the scope of science. So I'm going to deflect a little bit and not talk as much about truth in the same way that a philosopher might think about truth, even though there are some correspondence, areas of correspondence, and I'll talk about those. So in thinking about this topic a little bit, I first went to our old friend, the internet, see if this is going to work, and tried to get some quotes from the best and the brightest. Linus Pauling could be argued to be among the best and the brightest. And so Linus Pauling said, "Science is the search for truth." So that to me is fairly straightforward. Science is really searching for truth. Science is the process of trying to achieve truth. And so science as a process really has a particular goal, and the ultimate goal is this thing, truth. Whether that goal is achievable is a somewhat separate issue. I'm not sure that science can claim to achieve truth in the same way that a philosopher might define truth, for example.
But that doesn't mean that the search, which I think is integral to much of what natural scientists do, that doesn't mean the search isn't worthwhile. The search is actually, for many of us, the main thing, with the hope of, for example, achieving ultimate truth, perhaps not even being attainable. And I'll say a little bit more about that as I go along. There are various ways of thinking about how people search for truth. This is sort of one, oops, sorry, I gotta remember to click on that. This is sort of one representation of how people try to achieve truth. So there's a little bit of accuracy to this, and I'm not sure if you can read can you read the text sort of toward the back of the room? Forget about the spelling errors on the far right. I didn't actually create this. So depending on assuming that the elephant is the truth, the question is, how might you think about the truth? You have these different, in this case, blind philosophers who are trying to describe the elephant based on all these individual observations of some small portion of the element. And there's a certain amount of accuracy to this, I would say. Most scientists don't claim to be able to see the whole truth at any given moment in time. You're only able to see little glimpses into it. And the implication, though, is that the truth is there to be discovered if somehow those observations can be assembled into a holistic picture. And there's a certain amount of inference and induction that has to go into inducing the elephant from a bunch of very small and isolated observations that can often be very disparate. And so it's not too surprising if along the way one might come up with a version of the truth that is in fact false, can be in fact extraordinarily erroneous. And part of the search for the truth involves and acknowledges that there will be errors along the way, but in science, that's okay. Not every step toward the truth needs to itself be true. And that's something to consider. Of course, Carl Sagan said the sacred truth of science is that there are no sacred truths. That doesn't help too much. To me, in this quote, the term sacred implies that there's something that perhaps can't be questioned. And that's antithetical to natural science. Everything can be questioned. Anything can be questioned. It can be questioned at any time. So arguably, the only thing in science that can't be questioned is the principle that everything can be questioned. And that, I think, is how the average scientist views the notion of scientific inquiry. Isaac Asimov, science doesn't pervade. This is not going to be 20 minutes of quotes, by the way. It's not like 20 minutes of cat pictures. So science doesn't, if I'd only thought of that. Science doesn't purvey absolute truth. Science is a mechanism for testing your thoughts against the universe. So this would be proposing explanations for observations, making observations, inducing a proposed explanation for those observations, making additional observations that allow you to evaluate whether your proposed explanation is valid or invalid. If it's valid, it may suggest additional questions that you may want to pose. If it's invalid, then you may reframe your understanding of the observations with additional evidence and move forward toward a different test of a different set of explanations. So it really does imply, from my perspective, sort of the process end of things. One of the things I like about science is that it's sort of an endless process of inquiry and learning and more inquiry. Now, just in case you're curious, I started off, as I said, by looking at the internet, and I Googled truth in science. Have any of you Googled truth in science lately? If you do, you'll come up with this. This would be the Creation Truth Foundation's website. Creation Truth Foundation, by the way, is not a scientific organization, in case anybody was curious. The Creation Truth Foundation has this website, truthinscience.org.uk. It includes a curriculum that is science, notice it says, doing good science and be faithful to Scripture, which isn't always the main focus of a science curriculum. But this involves science curriculum. It's mainly intended for homeschooling, people who are doing homeschooling, to provide them with science curriculum that is still authentic to the Scripture. I wasn't able to actually download any materials from this website because that's all password protected, or you have to pay for it. But I thought it was kind of interesting that this is what comes up when you Google truth in science. There's also this website. This is Truth in Science Revealed. And I want to point out a couple things. I don't know how easy it is to read this, so I'll try to read a little bit. This is a universal model in new millennial science. For the last century and a half, modern science has been in a dark age. This claim will undoubtedly surprise many people, but it is true nonetheless. The reason for this bold claim is that modern science turned its back on the pursuit of natural laws when the theory of evolution was published by Charles Darwin in 1859. Since that time, scientists have been promoting theories rather than pursuing natural laws, which describe and predict nature. So has modern science really turned its back on natural laws? I would argue that those of us who do modern science, or at least purport to do modern science, actually spend a great deal of time not turning our back on natural laws and trying to understand, if not natural laws, at least the principles that govern natural systems. And hopefully those principles will both describe nature and predict nature, but there's a little bit of an element of validity to this last point. So descriptive studies do in fact describe nature, and there's a definite difference between descriptive science, in which somebody might go out into the world and try to describe what they observe, versus experimental science, in which you're testing a particular prediction or a particular hypothesis. And observations, descriptive observations, aren't usually subject to experimental validation. They're simply descriptions of what one observes, and they're subject to subjective interpretation. Whereas experimental observation at least gives you some opportunity to make a testable hypothesis and then evaluate that hypothesis in light of evidence that you collect. So there is definitely a distinction between those two areas. This is the last slide I'm going to show you from this site. This is the list of theories. This is a list of modern science theories that have replaced the laudable and important quest for discovering and understanding natural laws. And you'll notice the theory of evolution is at the very top. Right below it is the theory of relativity. The human theory, the theory of air. I'm not sure what some of these theories are. I don't know exactly what if anybody knows what the theory of water is, I would very much be interested in that. Yeah, right, the shape of water, but that's not on here. So one of the things that's kind of interesting is it says that all of these theories are false. It's a collection of pseudo-theories, which means that they are false because they are not based on empirical scientific evidence and therefore cannot be proven. And the reason I'm showing you this is because it gets at the issue of, is science trying to prove things? And for most of us, I would argue that science is not trying to prove things. Science is not about conclusive proofs, although Candice is going to talk to you in a little while about proofs, but not proofs as, it doesn't say anywhere here the theory of addition, the theory of multiplication, the theory of division. It doesn't say anything like that.
Those are true.
Yeah, because those are true. Yeah, exactly. And it also gets at the point that I think most modern scientists would make, which is that you can't actually prove theories. That's not the basic paradigm. The basic paradigm revolves around falsifying rather than proving, and Mitch is going to talk a little bit later about falsification. So I just want to make it clear that the scientific community doesn't consider scientific theories to be true because they have been proven. There's also the implication in here, in every case, the theory is claimed to be true because a majority of scientists believe it is true. That's also not the relevant standard. Certainly there are political elements to science, and anybody who doesn't believe that hasn't been paying much attention to climate change science recently. But the majority of scientists cannot make some sort of claim true in the absence of objective evidence that supports that claim. It's evidence-based, it's not popularity-based. That's not what modern science is all about. So I guess what you finally come down to, and Brian Cox is a physicist, not that that gives him validity, he's just a physicist. In science, there are no universal truths, just views of the world that have yet to be shown to be false. Okay? So that, I think, is a really nice summary of exactly where scientific inquiry tends to go. So what does science actually do? Science strives toward accurate, reliable understanding or knowledge of how the universe works. The scientific method is really an ongoing process. It's not directional. Pursuit of truth might be envisioned as a direction. You start off with a limited understanding or no understanding, and you move directionally toward the truth. But that's not really how science typically works. What typically happens is scientists make observations, think of questions, formulate hypotheses, develop testable predictions, gather data, and then if those support, or if those don't actually, the data don't actually support the prediction, then you refine, alter, expand, or reject the hypotheses. It's circular. If they do support the prediction, then you develop general theories, which leads you to more observations and so forth. It's entirely cyclical. It's not directional. And so it's not really moving toward the goal of truth. So let me think about this. And this is something I've been talking to a few people about and trying to think about a little bit. So how does understanding or knowledge differ from truth? One might argue that truth should be absolute. Speed of light is 3 times 10 to the 8th meters per second, more or less. Truth should be universal. It's 3 times 10 to the 8th meters per second, no matter where you are. And it should be eternal. It's 3 times 10 to the 8th meters per second now, and it will be 3 times 10 to the 8th meters per second 1,000 years from now, 1,000,000 years from now, and so forth. So that seems like truth. That's not necessarily knowledge or understanding. The way an ecosystem in the deep ocean operates today may be very different from the way it operated 100 years ago, and may be very different from the way it operates 100 years from now. And that's okay, right? It doesn't have to be quite so absolute as truth, in this context anyway. Konrad Lorenz, the founder of ethology, a field of behavioral science, said truth in science can be defined as the working hypothesis best suited to open the way to the next better one. So science is iterative, excellent, iterative and reiterative, and that's exactly the way it's supposed to go. It's not supposed to be about coming up with some truth that is absolute and eternal, etc. I'm going to talk a little bit, and then I'm going to wrap up because I think I'm running too long, yes?
You know my time, it's fine.
Okay, okay. So time is only relative. So in 1962, Thomas Kuhn published a book called Structure of Scientific Revolutions, in which he described science as proceeding through several different phases, and this is something that has helped to inform modern science over the last half century plus. First, there's the pre-paradigm phase, which is essentially the gathering of knowledge toward greater understanding of a particular system or particular observation. Then science proceeds normally through the accumulation of information in relation to a particular paradigm. In this situation, observations that deviate from the paradigm, it's not uncommon for those observations to be viewed as the result of errors on the part of the researcher. The reason why this observation doesn't fit the theory is because you screwed up in your gathering of the observation, and so the theory is probably right. Once more and more people start to gather information that contradicts the theory, accumulation of evidence leads to what's called a crisis period, and then researchers at that point start to consider alternative explanations that may conform better to the body of observations as opposed to a subset of the observations, and those ultimately lead to a paradigm shift, which results in the adoption of a new paradigm that explains all the observations rather than only a subset of those observations. And that's the general concept of how all this might work. And there are a couple of noteworthy examples of this. One is the transition from the geocentric model of the solar system with the Earth at the center and the sun and the moon and the planets revolving around it, versus the heliocentric solar system, which was a notion that was first put forward by Copernicus, subsequently bolstered by additional work by Galileo and Kepler, and eventually the body of evidence and the body of observation suggested that the sun does not in fact revolve around the Earth, that the Earth in fact revolves around the sun. But this was an example of a paradigm shift based on mounting evidence that the initial model of a geocentric solar system was simply incorrect. In my own discipline, not that I'm a marine microbiologist, as those of you who know me are well aware, but in the marine biology realm, an old question dating back a little over a century was whether or not bacteria are important in the ocean. And the paradigm originally was that bacteria were present in the ocean, but they weren't very abundant and they weren't very important in marine environments. And some of this was based on using standard biological methodologies. You go out to the ocean, you gather some seawater, you bring it into a laboratory setting, you put it on an agar plate that's used to culture bacteria, and then you put it in an incubator and you wait for things to grow. And time passes, and not very much grows, and so the ultimate conclusion is there aren't very many bacteria in the ocean. And then somebody thinks, well, maybe the ocean isn't actually like a petri dish. And maybe bacteria that live in the ocean don't actually grow on agar plates as well as maybe they might grow in, I don't know, a liquid medium, for example. And so eventually what happened is through a series of techniques, people became aware that if you took water samples from the ocean, brought them into a lab, put them in liquid media and grew them under more oceanic type conditions, more bacteria would grow. So maybe there are more bacteria in the ocean than we thought. And what that ultimately led to was people bringing samples into the lab and staining them in a way that would actually illuminate under a certain kind of light field that would illuminate bacteria. And people very rapidly became aware that there were on the order of 1 million bacteria for every milliliter of seawater, on average, for the ocean as a whole. And so that led to a paradigm shift in terms of marine microbiology, and I'll show you an example of how that plays out ecologically. The old example of a food chain used to be Phytoplankton are eaten by zooplankton, are eaten by larger organisms, and that's how nutrients flow in the ocean. And the reality is that once you start to do that sampling and use new detection methods, and it becomes apparent that bacteria are both abundant and important in the ocean, then the food web shifts to look more like this, where you've got phytoplankton, zooplankton, and fish, and this enormous extra section of the food web called the microbial loop that deals with all of the organic material that's released by the phytoplankton, released by the zooplankton, and microbes are incredibly important in the ocean. Not surprisingly, this has actually gone one step further. It used to be thought that there were very few viruses in the ocean. And for those of you in the room who are marine scientists, you know that's not true either. Turns out there are probably somewhere between 5 and 10 times as many viruses in the ocean as there are bacteria. So every milliliter of seawater contains on the order of 5 to 10 million viruses. Makes you never want to go swimming in the ocean again, right? So just by way of wrapping up a little bit, those are examples of how science proceeds, I think. So science never gives up searching for truth, since it never claims to have achieved it. And I will just end on this note. I would argue that in many ways, science actually requires faith, which is something that people don't necessarily talk about a lot. But you have to have faith that there is some truth out there waiting to be discovered, or else why bother looking for it? So even if the truth hasn't been discovered yet, scientists, I think, have faith that the truth is out there somewhere. They just need to do more work to learn what that truth might be. It's unclear to me that humans have to be able to understand that truth in order for the truth to be real. You could argue that many scientific principles are sufficiently complicated that the human brain may or may not be able to accommodate them all simultaneously. And so machine learning, for example, and artificial intelligence offers some tools to help perhaps probe for truth in a way that an individual human brain might have a hard time doing. But I would have to question whether artificial intelligence is really going to further scientific inquiry, in the sense that typically artificial intelligence only works with the body of evidence that is there before it and assembling it in novel ways. It's unclear to me that a paradigm shift, which involves the creation of something entirely new, is going to easily come out of an artificial intelligence scenario. So that's just something to think about going forward.
While this is getting set up, when Brian said I do not theory, it's like K-N-O-T, not N-O-T. That's just, people usually are like, so she doesn't do theory, what does she do? And it's just yeah, okay. I was thinking of something funny to say there. Okay, I appreciate the opportunity to speak about this. I also agree that time is relative. I like to say it's a social construct. So my students often feel like when I'm talking about mathematics, time just drags on. So I don't have as many slides as Ram does. But one thing, every time I get the opportunity to speak, I like to start off with a land acknowledgement. I think it's very important to acknowledge that the land that we're on is unceded territory of the Kumeyaay Nation. So I like to start off with a land acknowledgement when I speak. So I am going to be discussing what truth means in mathematics. I'm teaching history of math currently, and I asked my students, like, what do you think that this means to them? And, the first thing that comes up is this idea of proof, right? We have this idea of proof in mathematics, and once we've proven something, it becomes true. And so the definition, the proof theory is truth is logically deduced from other established truths of mathematics. So it's kind of convoluted, right? We sort of have truth, and then we use that truth to prove other truths. How do you do something like that, right? How do you use truth to prove truth? So in order for this to work, you have to have a set value of what truth is to begin with. And so we start off with what we call axioms. So we already have sort of this base of these things are just going to be true no matter what, and then we build from them. We'll build from these truths. So just some set of assumptions that we assume are always true and then build from there. And then from that, we can then build definitions. So once you have a definition, it is defined that that is what that object is, and we will always define it that way and assume that that is what that object is. And there are some definitions that we have to use because we can't actually write down what that entity is with numbers. So for example, some example definitions is pi. So there's not actually a way to write down all the digits of pi. Yes, we're comfortable with me saying that? Okay, so I mean, I think someone in some state passed a law that it's going to be 3.14, which, why not? Let's build things, let's just build things in that state, right? But the universal sort of truth or definition of pi is it's always the circumference of a circle divided by its diameter. That's the definition of what pi is. So that is how you can actually discover pi, is you measure the circumference and then you divide by the diameter and you get this relationship. And so that's how we define pi. And then e, which is also the exponential, which shows up in nature, also has this mathematical definition, right? We can't actually write down all the digits of e, but we can say, well, let's let e equal this formula, and then that's what we do. And of course, it's quite complicated. We're letting n go to infinity, which means it grows and grows and grows without bound. And what this number sits on is this value that we see in nature. So building on these axioms, then giving ourselves definitions, we can then prove things with the axioms and the definitions. We can prove things to be true based on these assumptions and these truths that we've decided to be true. But it's actually quite a flexible idea of truth. You get to make up the rules and then see what happens. So in mathematics, we make assumptions. Like, let's assume this is true, and then what happens if this is true? So it's much more flexible than one would think, because one thinks mathematics is so rigid. But we do have this opportunity to assume different things and then prove with those assumptions. So if we assume that we only are allowed to use two numbers, 0 and 1, what are the things that we can do with just those two numbers, right? We can only write numbers with 0 and 1. It gets quite complicated, binary. But let's assume that's our assumption. What can we do with that? So this idea of truth is actually quite flexible because we start off with assumptions. So we get to do that. And sometimes so this came up in our conversations. We can use simplified versions of things. So it's true in this case, but if we looked at the broader case, maybe it's less true. So let's just look at this very small situation. This happens a lot in math classes because you'll be learning something with your foundational understanding of mathematics, but to really understand what's happening, you need more higher math. And sometimes you get to another class and you're like, wait, that's why that works? And it's like, oh, well, yeah, we would have told you that, except you didn't have yet the knowledge you needed to understand that. That happens a lot. And that will change truth. That will change what true means if you have more information. And then sometimes we prove things with untruths, right? So sometimes we get to assume something is not true and then show, well, if it's not true, it breaks this other rule, and thus it must be true. So there's this thing, it's called proof by contradiction. So you define your conditions, and then your conclusion, you show that they contradict. So this is a big proof, a big choice if you're proving something like the square root of 2 can't be written as a fraction. Well, you start off and say, well, let's say that it can be. And what breaks? What truth am I breaking? And so it's interesting because in order to do this, in mathematics, you can either have true or false. There's no middle ground. Right? It's either true or it's false. It can't be sometimes true, sometimes not true. So if you contradict, that means your assumption of true was incorrect. This is the same with there's a largest number. So if we assume there's a largest number, well, the contradiction is take that largest number and add 1. Well, that number is now larger, but I said that the other number was the largest number. So there's the contradiction. I was trying to think of an example where this would work in real life, and I was talking to one of my colleagues, and I said, let's say that you're trying to prove someone didn't go to work that day, okay? And let's assume they went to work. So that means that they have less gas in their tank than when they started the day. But you check, and they have the same amount of gas. That's a contradiction. So they must not have gone to work that day. But that doesn't quite work in real life because they could always just get more gas, right? There isn't this true or false nature there. But with mathematics, it's either true or it's false. And so that's why we are allowed to use that. The other really interesting thing about mathematics is you have these ideas of truth in math that are not true in the world. There's no real way to describe how that works in the world. So for example, the Klein bottle is a true mathematical object. This is not something we could actually create in the real world. It sort of wraps around itself. We have this diagram of the arrows of the direction it goes in, and then it comes out, and there's not this hole. It's like this four-dimensional object that we're trying to do in 3D. But it's true in mathematics. We can create this object in mathematics, but we could not actually create this object in the real world, right? So there are these truths in mathematics. They're not worldly true. So how useful are they, right? They're very useful in mathematics, but if you went into a bar and asked for a Klein bottle, they would kick you out. They would kick you out because it doesn't make sense. The other idea about these not worldly truths are these paradoxes. And so one of the famous paradoxes is Zeno's paradox, which is this sort of argument about the turtle and the man sort of racing. So you let the tortoise go ahead, and then the man is running behind him, and he goes half the distance every time. The tortoise is always ahead because you can never catch up, right? You go half the distance, but the tortoise has gone further, and then you go half that distance, and then the tortoise has gone further. So the picture sort of looks like every time you're going half the distance that's left. So mathematically, you never get to where you're going because there's always more distance. Half of the distance is left every time. It's very weird to think about because it is not worldly, right? If I'm I'm eventually going to get there. You actually cannot just move half the distance. It's impossible, but mathematically, we can show that you never get there. So there are lots of these ideas of sort of counterexamples of worldly truth that are mathematically true. And so the relationship gets very interesting. And then one thing that Ron had mentioned was one of the ideas with science is that you're collecting data. So if you have an outlier, I think usually what happens with an outlier is you toss it out, right? Okay, mathematician. Okay. In mathematics, if you have a counterexample, that disproves everything. If you have one example that doesn't work, that means that your truth is not true. It is false because there's no middle ground. It's either always true or always false. So if you have one example that doesn't fit, then it must not be true. So it's very different, right? There's this different idea of what truth means versus science and mathematics. Yeah. So I'm really looking forward to the discussion we're going to have around this because we had a lot of good discussion about it. But yeah, so thank you.
I'd like to thank Brian for the invitation. I'd like to thank my director, my producer, my fellow actors. It was incredible. I couldn't have done it without you. It's unbelievable. Thank you. This is a challenging topic for a scientist, and Ron brought that up, and I think the three of us felt this when we met and talked it through and how we would display things. And so I don't like to follow the rules exactly, so I will kind of weave my way out of the question of truth into a couple other areas, and we'll see where we go. But I guarantee you I will tell you the whole truth and nothing but the truth, except for all the lies that I tell you. I tell my students I lie to them every day, and I do, and I'll show you how I lie to them every single day, and I'm not going to stop. I'm going to talk about scientific truth only very briefly, and then talk a little bit about models. How do we actually describe the nature of reality to our students, and then think in terms of metaphors a little bit, and finally maybe talk a little bit about the classroom and how the classroom plays out and so on. I want to start this way though, and give you a sense of how I sort of got interested in some of these questions about the nature of reality. I came to USD in 1984, so in the summer of 1985, I was teaching chemistry and society, so the general education and chemistry course. And in those days, there was a real presence on campus of priests and nuns, which is really not so much true anymore. And there was a nun in my class. And so the Sisters of the Sacred Heart had nuns come to USD from around the world, not a lot of them to get their degrees. There was a nun from Uganda, Sister Ursula. I've never forgotten her. And she was taking the class, and about the third day, this is summer, so the pace is fast. About the third day, she came up to me after class and said, I have no idea what you're talking about. And I'm thinking, geez, I know I'm kind of inexperienced, but I thought I was sort of doing okay. I mean, she said, I just have no concept of atoms and molecules, and what are these things that you're talking about? Because in my village, we do not have any concept of atoms. We do not explain the world using these concepts. It just doesn't register. It makes no sense. And I thought, whoa, I have a lot to learn. Because sort of as a trained chemist, I mean, we never had conversations about the nature of reality. We were accepting of atoms and molecules and bonding and structures and all those kinds of things without ever asking ourselves, are these things really true? And that was my first kind of dip into this thought of how inadequate I really was. And so I spent some time trying to really work my way through and eventually ran into Dennis Rohatton. If any of you know, Dennis was a philosophy professor. He retired a couple of years ago. And Dennis and I started teaching classes in the history and philosophy of science, and that's how I sort of got interested in this. But Sister Ursula was the one who really got me into this whole world. And the second little story I'll tell you is that I decided I wanted to teach in New Zealand last January. So I'm thinking, what kind of class do I want to teach? And I decided I would teach a medicinal chemistry class in New Zealand because there's a indigenous population, the Maori, and they have an alternative health system, which was banned for a long time in New Zealand, but now they're practicing it again. And I thought it would be great for the students to see Western medicine and compare it to indigenous medicine and how it all plays out. And so I did that. It was a tremendous experience, I think, certainly for me, and I think for my students. And I just wanted to show you one picture. This was a healer. So I had a whole series of Maori folks coming in the classroom. They took us out into the rainforest. We spent a lot of time together. It was a really wonderful experience. And these healers, this is one of my students. He said he had a bump on his head that had been there for a very, very long time. And so they decided that they would try to heal him. And she has on, these are kawa plants. It's an analgesic. It'll relieve pain. You can chew the plants when we go out in the rainforest. And so she was using kawa plants and a bar that she had to help him cure this. And my students would be like, Dr. Malachowski, like, can we really do this? I'm like, yeah, of course. This is the way other folks, we being other folks too, see the world. And this is how they will try to handle a problem of some sort. And it was very striking by the end of the time how much I think the students came in their understanding of the nature of reality and how we actually explore and explain the world. And I got pictures of students on the ground and they're getting massages and all sorts of things. But one thing I'll just point out that was very striking, and then I'll get on with this, was the first thing they say that they do if someone in a family gets sick, is they treat everyone else in the family. They start treating the person too, but they treat everyone else in the family because it's clear that when someone in the family is sick, everyone else in the family needs help. And it's a very striking way, and there are various ways that they would help others who we would consider okay. And anyway, so that's sort of how I got to where I am and thinking about these kinds of issues about the nature of reality. That's really what I'm interested in doing. So Ron did this already. I'll do this relatively quickly, but I'll simply say, what is science? I mean, some people say it's a collection of facts. Scientists say it's a way of seeing the world. That's really what we're doing. It's not a collection of facts. It's a way of approaching the world. You can use a deductive method, an inductive method. I can lay out an inductive method. You get some data, formulate a hypothesis, explain the data, maybe test it against the data, see if it fits. If it's good, then we say it's maybe true. If it's false, we say maybe it's something that we need to rethink. And then in the end, I guess I would say that truth then is an endless process of sort of give and take, back and forth, analysis, synthesis, theory, experimentation, and somewhere in there, there's truth. And I think for most scientists, we really don't think much about where that truth is. I mean, we don't call it truth in a sense, generally speaking. Ron spoke to Karl Popper's vision, though, and that's the vision of thinking about falsifiable data. So it's really about falsifying things rather than trying to prove things. You're really trying to disprove things. And in my research lab, we do that every day. We disprove things. We fill up waste bottles all the time. I mean, we're constantly disproving things, and those are called failures by most people, but Popper would call it a good science when that works. But it's not about finding truth, but rather discovering falsehoods. That's the Popper model. John Wheeler, the famous physicist, said, well, if that's true, then we should all hurry up and start making all sorts of mistakes, because the only way to move things forward is to end up in the wrong place. And that's how science will make some progress. But I want to ask this question, though, because the question of truth in science is a challenging one for most scientists. But I think the question that I would like to explore a little bit is, how do we actually have conversations, though, about science? How do we discuss science? Truth or not, what do we do? And I think that the first question is, do we actually use truth in terms of describing science? And Candice was talking about the fact that in math and certainly in chemistry, we don't always tell the truth. So as much as I told you I would tell the truth, I was lying. And basically then, what do we do? Scientists attempt to form a picture for the phenomena, and the chief way we do it is using models. So the real fundamental question in my mind is not what is truth, it's the way we describe reality to our students or to each other using models. The question is, how truthful are the models? Because the model is the way that we describe whatever it is that we're trying to do. So if I jump to chemistry, I'd say, well, there are a number of models. I'm not saying these are the only models, but there are physical models that we use. So I brought a physical model, so I can show you that, a ball and stick kind of model. There are atomic structures. I'll show you some pictures. I'll just show you one or two little pictures so you get a sense of that. And there's certainly theoretical modeling, that computational modeling, mathematical devices, and so on. So let me just sort of show you. This is something I did this morning. So I teach a class this morning. It's an advanced organic synthesis lab. 12 students, incredibly bright students. Most of them will grow, get PhDs. And I brought this in, and I showed it, and it had a different little version of it, but I said, what is this to them? I asked them what it was. These are senior chemistry majors. And they said, oh, that's cyclohexane. So they said it was cyclohexane. And I said, really? It doesn't look like cyclohexane to me. What are you saying? They said, oh, that's cyclohexane. It's got a carbon there and a carbon, and it's got this thing, and it's got a particular shape. You can see the shape, and I add a little bit to it. And I said, no, that's not it. This is cyclohexane. This is what cyclohexane is. This is actually water. I didn't think, it's not carcinogenic or anything, and flammable like most of the chemicals, but this is what cyclohexane would really look like. So what is this, and what is this, and what is the relationship between these two? That's really the fundamental question that I'm asking. And these bright students think that this is cyclohexane, and I will try to say by the end of this, that's the challenge. The challenge is when the model becomes what we actually think the reality is. And no student would imagine that this is what they would not say this is cyclohexane. This is what it is. So there are lots of models that you can use. We use all sorts of models. Here's another one. These are really expensive models, actually. These are CPK models, they're called, and they actually are machines, so that these are sort of the actual size of the atoms in relation to each other. The black ones are carbon, the blue are nitrogen. This would be some metal or something. And these things rotate in space, and they're really quite powerful. You can really, and I tell my students, even if it doesn't make any sense, they're good therapy. It's very therapeutic, you know, to handle them and rotate them, and you sort of see them. But this is a model. I could make a model of cyclohexane, and it would have some relationship to the model that I just showed. But this one's better. This is a better model. So some models are good, some models are not so good, some are better, some are worse, whatever. And that's really the point that I'd like to just sort of think through a little bit. The other kind of model is the one that we'll use all the time. If you pick up a textbook, there's a structure. We draw structures all the time. This is benzene. There's a famous little dream that Kekulé had about this, one of the more famous dreams in chemistry, I guess, I don't know. He saw a snake kind of coming over on itself and biting its tail, and he thought, oh, maybe the structure of benzene is a ring, which actually had been sort of hypothesized. He was not the first, but he figured out that the structure kind of the snake tied over on itself, close the ring, and so on. And you end up drawing the structure that way. So that's another model, and that's a very powerful model. If I said to my students, what's this? They'd all say benzene. That's not benzene. I'd pull out my water again and show you, what that thing really is. Here's another more complex one, but this is the language of science. This is the way chemists talk. This is the way we communicate, and this is the way we see reality. This is a compound some students in my lab made, and we were trying to make what are called metal organic frameworks. I might as well try to teach you a little chemistry while I'm here, because I don't really know anything about philosophy and truth. But we were trying to make these molecules, and you can kind of see these are atoms, supposedly. These are atoms, and different colors are different atoms, and nitrogens, and coppers, and irons, and things. And we were trying to make something that had cavities. We were trying to make porous things that you can bind things in the cavities and you can transport them or do whatever you want to do with them. And so if you look at this, you can see these are called ferrocene. Someone thought that was a clever name for this little piece, ferrocene, like a ferrocene wheel or something. But you can see in the middle of this a big cavity. If you can picture this thing kind of rotated like that, and this thing kind of rotated like that, big cavity in the middle of this. We can make different sizes, we can put different things in there, there's all sorts of things you do with these. But that's the way we communicate. That is scientific truth right there. That's chemical truth in the minds of most chemists. And the question is that really what this molecule looks like? Is that actually the nature of that? And that's the fundamental question, I think, that we need to ask. Where am I? I'm stuck. All right. There are those who then say what we need to realize is models are just models. The thing that we conjure up in our head is not reality. These are really models. The challenge, though, is we need to somehow use something other than physical reality, because physical reality is difficult to talk about. And so folks started to think through, not simply thinking of this as models, but thinking of them as metaphors. And so the question becomes, how do we express scientific concepts in an understandable way where we can communicate? And the answer is, chemically speaking, models, in a general sense, metaphors. Simple ball and stick models are capable of representing a whole lot of things. I showed you a CPK model, those are better, but the reality is they're simply metaphors for what reality really is all about. What is the language that we use? And the point becomes, how else are we going to do it? We lack the understanding or ability to describe molecular level entities and processes literally. I can't do it any other way. This is the best I can do. And so I'm going to use models and I'm going to use metaphors, and I would argue that in chemistry, essentially all models are metaphoric. And so they're metaphorical models, and that's the way we really need to think about this. What's true about the model that I just showed you? What's true about the mathematics of the computations that people do in terms of understanding what the world. Models then are useful for some things, but they are not, they do not accurately depict the entire, whatever it is we're trying to explain. But I think that we could say the same thing about metaphors, and folks in this room can speak to that much more than I can. But we have a whole sense of how these things actually play out. Max Black, who's written a lot about metaphors, says every metaphor is the tip of a submerged model, and I think that's really true. So when we think of models, we really think of our metaphors. The challenge for scientists then is it's really difficult to deal with the macrocosmic. How do we explain galaxies and solar systems and things way out there? And from the chemical viewpoint or the biological viewpoint, what about cells and molecules and atoms? The very big and the very small are difficult for us to get our arms around. So we'll use models and metaphors. Brian Arthur said non-scientists tend to think that science works by induction or deduction, but actually science works mainly by metaphor. And when I read that, I thought, that can't be true. And then I thought, oh, I think that's kind of true in terms of the way we communicate it, at least. I think that's true. Kuhn came along and talked about metaphors too. And so Ron put up some related kind of concept of Kuhn, and he said, that metaphors play an essential role in establishing links between scientific language and the world. Those links are not, however, given once and for all. Theory change in particular is accompanied by a change in some of the relevant metaphors and in the corresponding parts of our network. And you can see how that plays out. I just want to comment, you brought up the concept of climate change. I would say the folks who are the anti-climate change people are really clever. They're really smart because they don't talk about climate change. The paradigm shifted to climate change from global warming. So what do you do if you're talking against climate change? You call it global warming. And you throw snowballs in the Senate, whatever. Because you're smart enough to know that even though the paradigm shifted, you don't need to shift the conversation. You're going to talk about global warming, which is only one part of what people finally understood to be climate change. So the metaphor is really powerful, and you can manipulate it in the way that you need to do whatever it is. So I'm basically saying scientists use metaphors to communicate, and they really are important for us to do what we do. But the next point then is, a growing body of literature suggests that metaphors shape the mind, structure our experiences, and influence behavior. So we can talk about wormholes or electron clouds or atoms as miniature solar systems. So if you took a chemistry class, that might have been the way you learned about atomic structure, these electrons whirling around, this thing in the middle, it's like a solar system and everything. You cannot break that metaphor in a student's mind, no matter what you do. I guarantee you will never get that out of your mind if you're taking general chemistry. So it's not simply a metaphor that helps us understand things. It becomes a problem. The metaphor takes over, and you can't break it. And that's one of the challenges. So we need to create better metaphors, better models, and so on to get us beyond that point. So what we, am I going? I don't know how to use this thing, I guess. It's like science, it just goes around and around, and you never get out of this. So let me just make that point about, after a while, you sort of just accept that the metaphor is reality. So folks who talk about gravity think of it as a rubber sheet and something just warping the space-time around that sheet, or the universe, or the inflating balloon. If you think of the expanding universe, you think of a balloon expanding, and you can explain why there is no center, in a sense. The only problem with that is that's not really reality, but we start to get a picture in our head, and it prevents us from getting out of that and moving forward. That's part of the challenge of this. The universe is not a clockwork, it's not a drum, the brain's not a computer, black holes are not cannibals, and indeed, I'm told they're not even black. Black holes are not black, I'm told. But the reality is, after a while, that's the way we take it in, we internalize it, and that prevents us from moving forward. And that's the challenge, I think, with this whole concept. I just want to make one point about language then, and that is science is supposed to be characterized by precision in the absence of ambiguity. That's how we assume things go. Language of science is assumed to be precise and unambiguous. In this mindset, metaphors should rarely, if at all, occur. We shouldn't be talking like this. We should be talking in a more pure way about science and how it goes. And if you read about it, this notion sort of took root in the 17th century, in sort of the Galileo days. The rise of science coincided with a great interest, I'm told, on the part of many philosophers to the concept of the ideal or perfect language. So this is a tool for us to express concepts in a language that's precise, and that as science was growing, this mindset was growing. And Galileo writes of the universe as a great book written in the language of mathematics, which is the purest of the descriptors, of course, and that's how it goes. I'm going to skip that. That goes on too long, but I'll simply say. The notion that takes root then in the 17th century is one that is a great challenge to us. And why can't I will listen? Yeah, it's a great challenge to us. So I just want to wrap it up by making a couple of observations about this in terms of how we handle this with our students. Students assimilate what they're told into pre-existing conceptual frameworks, and this is the challenge. So whenever I'm up here, so I don't know, I'm teaching right now, I don't know what I'm doing. Let's say there are 30 of you here, like in my organic chemistry lecture, and there's no doubt there are 30 presentations going on right now, as there are 30 classes going on in my organic chemistry class at all times, because all of you came with whatever pre-existing conceptual frameworks you had, and I showed you this one, and you did something, I don't know what your brain was doing, I mean, but all of you processed it differently. And so the challenge becomes, how do we work with the fact that we all come with these pre-existing conceptual frameworks, and they can perpetuate misconceptions. And we need to be aware of that concept. Maybe we need to let the students in on the fact that we talk in metaphors quite frequently. I tell my students all the time, I lie to you every day. This is not what reality is. This is not what organic molecules look like. This is not what reactions actually look like when we do them. And I think it's important. The other way is to start with a low-level model, which I think is a common theme for us. You start with a low-level model, explain its strengths and its shortcomings, and really point out that it is a model. And there are things that it does and there are things that it really doesn't do. And then a series of iterations get us to a higher level of understanding. Is a ball really like an atom? So this is a ball and stick model. Is this thing really like atoms? These little black carbons here, these blue bonds, is that really? Could I make a better model? Yeah, people make a better model. They take these things and make springs, because molecules are in motion, so there's a motion. So that's a better model. It's a spring, and the spring is moving and vibrating the way the world actually exists. So that is a higher level kind of ball and stick version, and we can do that. Of course, we should try to have a conversation about what's hidden. What are you confronted with, but what are you not seeing? There are things here that I'm not displaying for you very well as you go. And then the other thing I'd say about it is, and I haven't made this point, but I'll simply make it, models are used for different reasons. So some models in chemistry are used for their predictive power, so they can predict something. Other models are used because they help us understand something fundamental. Some models do both. Let me give you an example. I'll ask you, I don't know, I know a few chemists in the room, and so I won't let you answer the question. Everybody else will have to answer the question. Here is a, what is this? It's a model. Good. This is not cyclohexane. Remember, this is cyclohexane. I'm going to drink my cyclohexane after when happy hour here starts, about 9 a.m. I think, when happy hour starts here. But all right, I'm going to ask you a little question. You can answer this the last thing you do. So this is a model, and it helps me predict. This is a nice predictive model. This thing will react, so I can change it around a little bit. It's going to react. Something's going to come in and attack this thing. So this is my hand, and then my hand is attacking this thing. And it's either can attack this way, or it can attack this way. So is it going to attack from the top, or is it going to attack from the bottom? So what would you say? It's going to attack from the bottom. All things being equal, because this thing's in the way. It's a simple, what we call steric argument, that's going to bump into that thing. It's going to prefer to do that. This is a powerful model to show students the predictive power of how reactions might occur. Unless this thing is also attracting. Oh, but if I change a little bit and attract, the thing that's going to get attracted, it's going to come on. So this is a very powerful predictive model that we use all the time. And I think that's really beneficial to think through this thing. And finally, models can sometimes be nothing more than tools. They are simply models, and they do nothing more than that. They sort of help us do that. And I don't know why it keeps going backwards. I'm going to finish if I ever get to the end of this. So I guess I have to finish by asking what is truth, since that's why we're getting paid so much to come and speak, to talk about truth. Yeah. 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 I guess the point is, Dennis and I, a long time ago now, wrote a piece about half-truths, like the nature of half-truths, which sometimes are called lies. But we need to tell a series of half-truths. That's really the way we do our business. That's what a model is. It's a half-truth. But we hope the sum of the half-truths gets us somewhere to the whole truth. I don't know how the math adds up there, but 6 or 7 of these half-truths get us to a whole truth. And it's because we have a really difficult time revealing truth all at once. It's really difficult to do. We need some little bite-sized pieces to do. And I'll finish, and this is for Brian, truth be damned. That's what I'd say about this at the end. And I'll just make a case for science. The primary condition for doing science is not the respect for the truth. It's the will and daring to imagine the world as other than it is. And truth be damned, I guess, is the end of what I'd say. So I'd say thanks to my colleagues and thanks to everyone here. And we'll open it up for questions, I think. Ron can run this.
We're going to go left to right, I guess. Yes.
I want to start with the picture of the elephant. I mean, you're looking at parts. It seems to me science has this problem. I mean, we all want to understand the world, okay? And so now it's developing this sort of like foundational thing where you build up rather than giving you the picture of the whole, you build up and therefore eventually you get the whole. And that's necessarily a constructivist model, right? So it leads to another problem because this building up is so complex that it breaks up into a number of realms and disciplines. And so even if each discipline was pretty complete in its own, you need to like stitch together these separate fields of knowledge in order to get the whole elephant, right? And although science is beginning to break that model a bit, the silo model a bit, there doesn't seem to be enough attention paid to interaction between the various models to stitch together something that you could present at least some semblance of the whole, because that's actually what we want to know, how the whole works, rather than like these bits of information that who the heck knows, because it's always so complicated already. You add that other layer of putting it together. In the old days, I mean the very old days, it starts from the fact you already had a whole. It was false, but like God created the world, that's a whole, and there are these parts you put together. Okay, I understand what the whole is. Is there a way that science could solve that by creating, let's say, at least ambassadors between the various things to stitch together these realms of information so it begins, or at least give a kind of vague image of what the whole might be?
So I would say, I mean, procedurally, that sort of thing happens. Just to go back to the climate thing, if you want to understand the Earth's climate system, you can't just do that as a pure physicist or a pure chemist or a pure biologist or a pure geologist or a pure, you name it. You can't do it as a pure anything. And the models that currently exist, the representations of reality, or at least our current best understanding of representations of reality, which everybody acknowledges are incorrect, but better than nothing, better than they were 5 years ago, but still incorrect. Those are going to have pieces that are going to be worked on by people from different disciplines. So if you're interested in like the molecular chemistry of clouds, which is an extremely complicated field all by itself, that's something that people who are expert in that area have to work on. And then the goal is to find the people who are interpreters, if you will, the synthesis people who can take understanding from different subdisciplines or different disciplines and try to integrate them in a way that's correct and authentic. And that's challenging in and of itself. So science, it's interesting because there's been some literature that suggests that science that's done by teams, large teams especially, may be very good at certain things like building climate models. But they may be very bad at certain other things like innovation. Sorry, Brian. They may be very bad at things like coming up with new ideas or challenging existing paradigms. And so now you have this paradox. Because if you want to understand something complicated like the Earth climate system, you have to get a lot of people involved with a lot of different expertise. What are the chances that they're going to come up with some new idea if the pre-existing framework is wrong? And so it's challenging. There need to be more philosophers involved in doing science. Oh, wow.
So, today, on my phone, where all truths are discovered, I read this, I don't know if you saw it come up on your phone, but it said that the universe is now probably growing and expanding much faster than we thought it was. And we're gonna have to redo all the calculations. I don't know if you saw it. So, and this is the question is probably gonna ask you to start the presentation all over again. But is this an example of a paradigm shift? Is this an example of that they're gonna have to sit around and use new models? Is this that they need to do different hypothesis testing? What is the process? What kind of science are they going to use?
Well, I mean, you know, the concept of a paradigm shift is not clear how far you have to break away to. My guess, and I don't know what the mechanism is, I don't know what the new mechanism is that they're describing that's happening, so I don't know that. But you know, a paradigm shift, an easy one would be the universe is not expanding after all. That would be clearly a paradigm shift. So expanding at a greater rate, using the same mechanism, but the numbers are wrong, whatever, that would be science as normal science, with some problems that are associated with that. That would be my guess as to how it plays out. But it's fascinating to think, first of all, that you could ever calculate how fast the universe is expanding. The amount of information needed to do that and is remarkable. But I would say that's kind of like business as normal with some mathematicians doing some better calculations, you know? I mean, I don't know what you
Better
think.
tools, yeah.
Mhm.
Yeah, I agree.
Yeah.
So I have a question about teaching. So Candice had mentioned that in order for us to realistically talk about truth in science and math, we need to lay this groundwork, right? And so a lot of, in biology anyway, our intro series is about, here's the structure of a cell, and here are the postulates of evolution, and here are these things. And the students take them all in as facts. Fact. I'm gonna memorize all these facts. And then they get to like the 300 level, and we're like, okay, now be creative in science. Now challenge everything that was in that intro textbook. It's all fake. It's all, you know, science advances by falsification. And their minds are blown because all of their high school experience and the intro series here is about giving them tools to then challenge truth, right? But they take them in, and a part of that's the educational system before us, right? We can't fix that. But how do we fix it here? Like, how do we structure our intro series so that we can convey, these are tools that you'll then use for better stuff?
So, yeah, I don't agree that this is the best way to do it. I just want to say, like, it's just how we're doing it because it's our educational system. I think one great thing that's being included now in our in pedagogy is inquiry, right? Where we're letting the students sort of like discover things or discover how things work and discover false truths or half-truths and figure out how much of it together becomes a whole truth. I think if we do more of that, where we're not just giving them these, okay, here's the tools that you'll need in order to solve this problem, but having them help them discover the tools that they need and maybe even showing bigger picture. This is actually something we talked about when we started talking about these half-truths, like we are lying to our students and then, well, when you learn more information, you can go further and actually see what this really is. How do we combat that? And that was one of the things, maybe we just tell them the truth at the beginning and then break it down, show them the whole elephant and then piece by piece. But I think that's also very hard to do because what is the whole truth? Especially because it's changing.
Yeah.
So.
I mean, I'd add one other thing to it. I think we do a really good job with our students with problem-solving skills and critical thinking skills, and that's what we talk about over and over and over. What we do really poorly with our students is creativity. And my next NSF grant is going to be to set up a Center for Chemical Creativity. That's as far as I've gotten with the idea. I have a name, but yeah, I need help. But I think this concept of creativity, which is what you're really expressing, innovation, all of a sudden, go ahead and innovate. You're a junior now. You're ready to innovate. Oh, wait a minute. What? So I think getting at this concept of creativity, and I do it with my students, and it's really hard. I've kind of backed off a little bit, but your point's a really good one. Yeah.
There's one more question over here.
So my question is, you talked about models and metaphors and a question about a related concept. So my thesis committee, oftentimes there were certain individuals who would say to me, what's the mechanism? You need a mechanism. You can't publish until you have a mechanism. And I would ask, what do you mean by mechanism? They would say, well, a mechanism. And so I started to read and think very deeply about this, because on one hand, it was something that seemed all important. On the other hand, nobody could clearly define it. So I'm curious whether you think, like, what role you think mechanism plays in scientific truth, and can you have scientific truth in the absence of a mechanism?
You know,
Yeah,
mechanism
even if you
is
want to tell me what it is.
Yeah, I mean, it's another model for how something went from here to there, and not knowing exactly what in a chemical sense, typically our mechanisms are, how does A get to B? And we try to work through how that happens. And they're all the models that we pile into that get us to B eventually. And we have a picture in our head that that's exactly what happened, that was the process. When of course, that really wasn't the process. That probably wasn't at all what happened. But we make one up because it's a predictive thing. We take a piece from here and a piece from there, and we know if we put them together, it will predict what happened, how we got to be. So it's a very useful predictive model that is probably nothing more than a model. And that is a metaphor for what happened in that process. That's the way I would see it. So whether it's explaining a static property of a molecule or a molecule in motion doing something, it's still a metaphorical way of describing it, nothing more.
I think there are some examples of truths where we don't understand the mechanism, and the goal of the inquiry is to try to elucidate the mechanism. I mean, I'll give you, this is a stupid example for a question that I absolutely can't answer, which is, I told you that the speed of light was 3 × 10⁸ meters per second. Why? Why isn't it 2 × 10⁸ meters per second? I have no idea. I don't think anybody knows the answer to that question. But my point is, there are lots of examples of more like simpler truths, if you will, where somebody makes an observation, the observation is taken to be accurate or reliable, and then the process involves trying to understand the observation. So elucidating the mechanism becomes the central part of the inquiry. Yeah, Malachi?
I just want to firstly say, firstly, apologize for my semi-preamble. I want to then shift immediately into a thanks and say how much I enjoyed your presentations and how exciting they were and provocative, because among the 30 presentations you guys were giving, one was entirely about poetry. That's fantastic.
She's great. She's wonderful. Great job.
Well, I want to ask you, I guess, when I think of what constitutes objective truth, I sort of think the aspiration is to move beyond the parameters of individual experience. And that's what testability means, is that what I perceive and how I experience X or Y detail is then confirmed by someone else, and you say, okay, great, it's not locked inside of the body. But one of the magnificent things about the talks you guys were giving was demonstrating, much as it might be frustrating for those who aspire to a kind of coalescent vision of the world, how much privacy exists within the languages of your disciplines, and how much that privacy is informed by your lexicon, by your metaphorical systems. And while it may be a frustration that in our effort to bridge the distance between selves, we wind up creating new boundaries of privacy around our various lexical enterprises, I wonder if you really think it's possible for us to aspire to bridge the distance between bodies and anything other than figurative, non-literal, metaphorical ways. Like, that may be an Achilles heel, but is it also the only way we get there? Like, as close as we can get?
Well, I mean, I'll answer it in a practical way, which is not really answering your question, but comes to mind. Noelle's here. People have talked about breaking the college into the College of Science and, arts and letters or whatever, and maybe some days Noelle goes, God, I wish we could do that or something. But keeping us together, gives us the opportunity to at least have these kinds of conversations. That's not the answer, but that's part of it. I think that there was a time, we tried years ago to start a science, technology, and society program, for example, at USD. It fell flat for a number of reasons, but that's the kind of thing, an intellectual connection that may not be so obvious. In many ways, the science building is beautiful, and it is, but I come in and I go to the science building, and I hang out in the science building pretty much all day, and it was one of the worst things that ever happened to me, frankly, as beautiful as it is, because I limited myself about moving around and having these things, but you know, in a practical way, team teaching and all those things, honors program, team teaching and things, if that's the answer to, I don't know if that's the answer, but I think first of all, valuing that, believing that that's important is the first step to trying to make it happen. Yeah. And that's absolutely right. We're here because of that.
Susie?
Well, I was just, to continue with Malachy's observation and what we were talking about in UCC today about the BS and the BA degree. And it's interesting because hearing the faculty talk about how our alumni are going into the field without a BS and being somehow handicapped by that, in the sense that the way the world perceives the degree is that it's not equal to a BS. A BA is not equal to a BS in something like environmental and ocean science. And while I am all in favor, obviously, of a department deciding this internally and that sort of a thing, I think that this raises the question of, outside of USD, with all of these beautiful intersections that we want to make, it still seems as though the natural sciences, mathematics, etc., these are where truth is privileged. And so with the liberal arts or the humanities, social sciences, truth is not looked at as being as valuable in the wider world. And so there's this question, but this is why I think with Malachy, I really appreciate all of your perspectives, in the sense that what Mitch was doing too, was very similar what we do in theology and religious studies. We create a model and then we test it out. And students, focus sometimes way too much on the model as being the truth, when we're trying to say, no, it's just a model. So it's interesting to hear you talk the same way in the sciences.
But we do it to them.
Right,
We're the ones that want it.
but see, I think in the wider world, when they leave campus and they try to, make this degree work outside of campus, and I understand that they might need the BS in that sense, but I am concerned about how truth is perceived in the wider world because of that, and because of the sense that, if you know truth through the natural sciences, then you're more intelligent, or you're more with it, or you have it better than those of us in other disciplines. And so I'm thrilled that all three of you focused in the way that you did, but again, this is the problem. We leave campus and...
If I can just build on that from something
Yeah,
that came out in
just because
UCC today.
So one of the things that people talk about is the critical importance of the core curriculum. And I would argue that the core curriculum has a value in numerous aspects, one of which is to make students critically aware that just because they think they understand the truth in their science class does not mean that they understand the truth at all. And they need to understand what truth is. They need to understand that there are different truths. And this is just something that flitted through my brain a little bit as I was preparing this presentation and trying to sort through an enormous array of thoughts and notions. It occurred to me that, so this is the third of a series of presentations on beauty, goodness, and truth. Beauty is clearly subjective and differs across disciplines. Goodness is subjective. Is truth not also subjective? And that's not the realm of the sciences.